We're going to get ready today to do our buffer capacity lab with our acids and bases of weak buffer solutions that have a conjugate acid and a weak base. So what we're going to look at is a quick review on what an acid and a base is, and then we're going to move right into what buffers are. So as a review, an acid can be defined in two different ways. We've got the Arrhenius acid. Arrhenius acid is a substance that produces H+ in an aqueous solution. So it's in water and it makes an H+. A Bronsted-Lowry it defines an acid as a proton donor. Now, a proton is an H+. So if it's a proton donor, then it donates this, which is essentially the same as an Arrhenius acid. Okay. And then what we're going to have is a base. And as a review, a base is similar to, it's exactly opposite of what an acid is. An Arrhenius acid, or an Arrhenius base is a substance that produces OH in solution or in water. So in a solution of water, a base is going to give you this. Arrhenius defines it as that. Bronsted-Lowry defines it as a proton acceptor. So it's one of these acceptors. So it's two different definitions, but it means essentially the same thing. It's dealing with the H+ ion either coming or going. And the OH in solution can be exactly the opposite. So, say for an acid, in HCl, which is almost always in an aqueous solution or anything that you would deal with, you would have water that goes to H+ and Cl-. Now, this is how, of course, water is a liquid, this is going to be an aqueous solution, and this is going to be an aqueous solution. Arrhenius defines this because it gives the H+ ion, it defines it as an acid. Bronsted-Lowry says that in water, that water itself acts as a base. So in this same solution, you would have HCl, of course in water, plus your water that's in solution. This is going to act as the acid. This is going to act as the base. And when it goes into solution and separates out, you're going to form a hydronium ion in water plus the chlorines in aqueous solution. So this is going to act acid, base. This is your acid and this is your base. So you have an acid and its conjugate base, and here you have a base and its conjugate acid. That's going to be important when we're talking about buffer solutions, because with buffers, you talk a lot about acids and their conjugate bases. So, with all this, there has to be an ionization constant because we're ionizing components. So, the ionization constant for any acid solution, say we have a general reaction. Let's go with HA plus water. And of course we are in water. Goes to H3O plus in solution plus A minus. That's just like our HCl, but it's going into solution. Okay, so for our general ionization constant for this general reaction, we're going to you always put the products on top and the reactants on bottom. So we've got H3O plus concentration of your hydronium ion, your concentration of your base, over the concentration of your acid. Okay, in any of these reactions, remember that we leave water out because it doesn't typically actively participate in the overall reaction. So this is going to be our ionization constant for any acid reaction. Okay, so we've got all this information. We've talked about this before. This is nothing new. This is not new material. But now what we're going to talk about is pH. And pH with respect to acids and bases. So we know that the pH of a solution depends very much on the H plus concentration. That's what it's based on. That's what the reaction calls for. So the pH of a solution, say that we have an HCl solution and we know that it's 1 molar. Okay, we want to determine the pH of that solution. What we would do, the reaction is pH equals the negative log of that H plus concentration. Because HCl completely dissociates, that means that we have 1 mole of H plus and 1 mole of Cl minus. Okay, so for this reaction, for this particular example, the pH would be the negative log of our 1.0 molar HCl. Okay, or you can just consider that the H plus. Okay, now we know that a pH equal to 7 is neutral. A pH greater than 7 is basic. And a pH less than 7 is acidic. That's important information when you're thinking about buffers and the different things that deal with that. So we know how to calculate the pH if you're just looking at a weak acid and you use your ice chart that we've talked about, initial, the change, and an equilibrium. And you calculate those different areas within that ice chart, but I'm not gonna go over those. Okay. What we're going to talk about today as we lead into our lab is buffers. And buffers are solutions that are made up of that acid, but it's a weak acid. So it's a weak acid combined with its conjugate base. So a weak acid that we'll deal with is, say, acetic acid. Acetic acid is a weak acid, and so its conjugate base would be sodium acetate. So a buffer solution is made up of both of these components. They don't just accidentally happen. You have both of them in there. So we would have H3O2, acetic acid, plus your water in solution. And it's not going to go to completion like a strong acid. It's a weak acid, so it's going to have that double arrow. Now, what it's going to form is you're going to still make your hydronium ion, but you're also going to have this sodium acetate, or this acetate component. So you're going to have your C2H3O2. Okay, so we've got our acid. This is acting as a base. This is our conjugate acid and our conjugate base. Okay, so what we do is we add this into the solution so that we've got both this and these components in that buffer solution. So what happens is when you bring those together, say I were to add some HCl to this solution. If I add HCl, that's going to make this component more acidic. So if I'm adding HCl to this overall reaction, it's going to go in, of course, as the hydronium or as that H plus component, remember? Because these can be used a lot of times interchangeably. So it's going to go in. When we're talking about equilibrium, things shift around. So when this goes in, that's just like a balloon. It's putting pressure on this side, and it's going to shift things back to the reactant side. That's what happens when you add HCl. But if I'm adding base to this reaction, say I add NaOH, what it's going to do is it's going to form a water molecule with this H, and it's going to make more of this in reaction. So that means I'm putting stress on this side of the reaction. It's going to kick it toward the products. So if I put base in there, that's going to kick this more so to the products. So it gives it kind of leeway. What buffers do is when they do that, it kicks it one way or the other and levels out again. And so when it does that, you can kind of keep a steady state. That's important for a lot of reactions, particularly within our body. Our body does this a lot with, say, sodium bicarbonate. And other reactions, but I'm not going to tell you about those. I want you to look into them. What I want you to do before we do the reaction this week, I'm going to give you a roll of pH paper. And what I want you to do is I want you to go home and I want you to test different things for their pH. Then, if you can find just one buffer solution, I want to know about it. I want to hear about it however you want to tell me. You can write me a little paper. You can show me a video. You can show me what reaction we're going to use, but I want to hear about those different types of buffer reactions that you come across. Okay, now for our experiment, what we're going to do is we're going to use the Henderson-Hasselbalch equation, and it's similar to our pH equation. So for our pH equation, we know that the negative log of the H plus is how you determine the pH of a solution. Well, Henderson-Hasselbalch, there's a long derivation, and I'm not going to run over it with you. We'll do that another time. But Henderson-Hasselbalch shows us that with a weak acid, weak base, we can take the ratio of the base to the acid, and that will give us what the pH is of the solution with respect to its Ka value that we talked about, the ionization constant for the acid. So the Henderson-Hasselbalch equation, it is the pH equals the pKa plus the log of the base over the acid. So if we're doing an experiment, we know the pKa of a solution. We can look up the Ka. If we just take the negative log of the H plus, that gives us the pH. So to get the pKa, you just need to take the negative log of the Ka value. That we know. We don't know the pH, and that's what we're going to be looking for. Or we might know the pH because we can measure it. So it's kind of a two-way process. What we may not know, or what we may know exactly, is the concentration of the original acid, which normally we're going to know, but we may or may not know the concentration of that conjugate base. And so if we can solve for these different elements, then we can get those final elements through the equation. Okay, that's going to be important to our reaction overall. Now, for our experiment today, or this week, rather, for our experiment this week, First off, you're going to start off with a group of buffer solutions. And what I want you to do, from the chart that you're going to have in your lab, I want you to pick 3 buffer solutions, the acid and the conjugate base. I'm going to use the generic right now. Okay, so we know all of this is in water because nothing is happening outside of water right now. Okay, so we've got our reaction, and I want you to choose from the list 3 acid and conjugate acid, 3 acid and conjugate base reactions. So we're going to use these, and I'm going to have 3 test tubes. And in those 3 test tubes, I'm going to make my buffer solution. So I'm going to get the pKa from the table. I'm going to determine what pH I want it to be at. So if I have a solution and we want to make the pH 5.4, I'm going to use my Henderson-Hasselbalch. I'm going to use my ratios to make, because I'm using 0.1 molar of whatever material we're using. If it's this, all of our solutions this week are 0.1 molar. So, got a 0.1 molar. I'm going to use my Henderson-Hasselbalch. Remember, pH equals pKa. pH equals pKa. Oh, now I forgot. Plus the log of the A minus concentration over the concentration of HA. So, we've got those values. We can put our pH in here, because that's what we know we want it to be. We know that our solutions are 1 molar, so we can put that information here, and we also know our pKa. So we will know what ratio we want to put that in to get our desired pH. Okay? So we've got our 3 pH ranges, we've got our 3 solutions. We're going to make these reactions, and what we're going to do is we're going to take the pH. We're going to use our electrodes with our pH meters to determine the pH of the solutions. And then drop-wise, we're going to add a little acid. So I'm going to add acid until I get a large jump in the pH. At that point, I know that I've exhausted my buffer. I've gone outside of the range which it can easily equilibrate. So I'm going to write that material down. Then I'm going to also add, I'm going to make 3 new buffers, and I'm going to add base to those. And I'm going to do the same thing as I did with the acids and take those values. Then, part B of the reaction. Part B of the reaction, we're going to use a triprotic acid, which just means that it has 3 hydrogens. It's phosphoric acid, and it's H3PO4. Now, that just means that it has 3 times that it can lose that H plus ion. So, what we're going to do is we're going to do a titration like we've done before with a flask. And we're going to titrate it just like we had before. However, the difference with this one is that we're going to use our pH meter. And we're going to use the meter to check the pH. So when we get that large jump or that large change in pH, we know that we've hit that equivalence point. So what you're going to do is you're going to end up with lots of data, and from that data, you're going to make a graph. And that graph is going to look something like this, where you've got 3 areas of equivalence. And it talks about in the lab where you get the equivalence point at half of the slope. And so you're going to do that. I've got another video that shows you how to graph that data in Excel, so look at that before you show up to lab. Make sure that when you are getting ready for the lab, of course you read the lab before you show up. Make sure you read it thoroughly. Make sure that you understand the material. If you have any questions, please let me know so that we can talk about it. We can do that over the wiki, or we can do that face to face. Either one, whatever you'd rather do. But Once you get your data, once you understand how to graph everything, then I want you to look at our pH video. The video shows you how to use the pH meter correctly so that you can do this part of the experiment, part B, and so that you can also do part A with the different buffer solutions and exhausting those. So, look through all the material in the book. Make sure you finish up your questions at the end of chapter 16, 1 through 53. Only do the odds. Make sure that you do those so that you can check those. If you have any questions, come see me.